So in the last few videos we've talked about the standard and general forms of a quadratic function. The standard form looks like this. And the great thing about the standard form, of course, is that we can see from the equation what the vertex is. That would be P comma Q. And we know that A tells us the direction of opening, upwards if it's positive, downwards if it's negative, and if the absolute value of A is more than 1, the graph is skinnier than normal. Between 0 and 1 for A means the graph is wider than normal. So this has to do with the stretch or compression vertically. So standard form is great because there's a lot we can tell about the graph of the parabola from the equation. The general form is what we started the unit with, and that was y equals ax squared plus bx plus c. And in both of these, by the way, a cannot be 0. A, b, and c are real numbers in the general form. And the a tells us whether it opens up or down, because it's the same a as in the standard form. But that's about all we can really tell. The only other thing that is handy that we can get quickly is the y-intercept, because when x is 0, y would be c. So c is the y-intercept. So the general form, like I say, we can tell the direction of opening, up or down. We can tell the y-intercept, but we can't tell find the important thing, which is the vertex, which really helps us position the graph and graph it accurately. So what we want to learn today is how to transfer between these two forms of the equation. Alright, so let's do the easiest thing first, and that's to convert from standard form, a x minus p squared plus q, into general form. So general form just means the equation is multiplied out and organized according to degree, second degree, first degree, and 0 degree. So to translate this into general form, I need to expand the binomial. And x minus 3 squared, remember, you can write that out twice and FOIL it. In fact, maybe it's worth doing, because this is going to be connected to the next thing we do. We get x squared. We get minus 3x twice. And then we get plus 9. So we get two sections of negative 3x, so we get x squared minus 6x plus 9, and then plus my 1 on the outside. So remember, and you've talked about this before, to expand a binomial, the shortcut is to square the first term to get x squared, multiply the two terms, negative 3, double it, because there's two of them, as you can see here when we get it the long way, so minus 6x, and then square the negative 3 to get plus 9. Alright, so now we can distribute and combine, and this is my equation in general form, ax squared plus bx plus c. I know that this parabola opens upwards because a is positive. It's skinnier than normal because a is more than 1. The y-intercept of the graph is 19, but I don't know the vertex. So, but if I look back at this equation, which is the standard form, these two are obviously the same. They're algebraically equivalent. In the standard form, I can see the vertex. Alright, so now that we've talked about going from standard to general form, let's talk about going the other way around. And before we get into the details of that, we just need to practice a few things related to binomial squareds and perfect trinomial squares. And this is what I was talking about in my last example. If I square this out, I square the first term, I will get 3x twice, 6x plus 9. Okay? And this is what we call a perfect trinomial square. I'll abbreviate it like that, because it factors perfectly into something squared. Alright, x minus 4 squared is a binomial squared, and if I work it out, if I expand it out, square the first term, x squared, multiply the two terms, negative 4, double that to be negative 8, and then square the negative 4 to get 16. And that's my perfect trinomial square. It factors back into that. Now what we're going to want to be able to do is to recognize a perfect trinomial square so that we can turn it back into a binomial squared. Because you'll notice that binomial squareds are the kind of thing that appear in the standard form of a parabola, ax minus p squared plus q. This binomial squared is a crucial part of that. So in terms of recognizing a perfect trinomial square, you'll notice that in both of these trinomials, the first and the last terms are perfect squares. And that has to be to have a perfect trinomial square. Now the middle term has to be double the square root of the two end terms. So these two end terms were x, their square roots were x and 3. And because when we expanded the binomial, there were two sections of that, in order to work backwards, we need to have 3x doubled as the middle term, 6x. So in this one I have a square root of x and a square root of 4. And what makes it factorable back to a binomial squared is the fact that the middle is double these two square roots. Alright, let's just practice this pattern a little bit. We want to fill in the blanks here so that the following are perfect trinomial squares. Okay, so what we're saying is we want to create a trinomial that will factor as a binomial squared. And I'm actually going to start with a second example, because here I have my two end terms given in my trinomial, and you'll notice that they are both perfect squares. The square root of x squared is x. The square root of 144 is 12. And then when I expand my binomial, I know that the middle term here will be double these two terms. They'll be double the square roots of the two end terms. So this would be minus 24x. So this will factor back to x minus 12 squared. Alright, so let's go back to the first example now. Now this is a bit trickier because we don't know the last term, but we know the middle term. Well, based on the pattern we just talked about, this term is double the square roots of the two outside terms. So before I doubled to get negative 10, I must have had negative 5. So that would have to be minus 5. And then when I square that, I get 25. Alright, so I'm looking at this pattern back and forth in terms of trying to get what I need. If I square this, I get x squared. If I multiply and double, I get negative 10. And if I square the last term, I get 25. Alright, now this pattern is the basis of what we're going to use in terms of writing a parabola given in general form into standard form. And this process is what we call completing the square. We have to create a binomial squared. Alright, so we'll go through a couple of examples here. First thing I'm going to do is I'm going to factor out of the first two terms the coefficient of the x squared. So in this case it's 2, and I then get x squared minus 6x. And then what I'm going to be wanting to do here is create a perfect trinomial square. So what I'm going to do is I'm going to put plus something and then minus something, because when I can't just put any old number in without adjusting for it, otherwise that would change the equation. So I'm going to add a number and subtract a number, and we'll talk about that in a second. The plus 19 is just sitting out here on the outside. Alright, so here we go using the pattern we just talked about. To make these first three terms a perfect trinomial square, this last number we can get by taking half of this, which is negative 3, squaring it to get 9. Right? The square root of both of these is 3, doubled is our 6. That's the reason we're doing that. Now I added 9, but I got to take away 9 to keep the equation the same. Alright, and you say, well, okay, I get that, but that's going to create a problem here, isn't it? Okay, what we're going to do now is we're going to group the three terms that are our trinomial square together like that. And now this minus 9, which is really 2 times minus 9, is negative 18 on the outside of the brackets. Alright? And so y equals 2. This is a perfect square. Okay, because we created it like that. We completed it to be a perfect square. So that's going to be x minus sign square root of 9 is 3. Check it out. Multiply these two together, double to get 6. Yep, that works. Plus 1. And guess what? We have our parabola in standard form. Ax minus p squared plus q. Alright, let's just do a couple more to get the hang of completing the square. So the first thing I want to do is factor out the coefficient of x squared. Well, the coefficient here is 1, so we don't need to worry about anything here. We just have x squared plus 8x. Now, we want to have a number that completes the square. Well, it's going to ignore the 1 for now. X squared plus 8x plus something. Now, to keep things in balance, we have to take away that something, and then we still have the plus 1 sitting there. So we're looking for the magic number here, so that this is a perfect square. Alright, and so we know that these two terms doubled have to give 8x. So to work backwards, we'll take half of 8, which is 4, square it, which would be 16. If I add 16, I got to take away 16 to keep things in balance. Alright, so these three terms factor to a perfect square, x plus 4 squared, and the constant on the outside is minus 15. And so we know that our parabola has a vertex of negative 4, negative 15. Alright, one last example. Perhaps try it on your own, stop the video, and then start it up again to see how it goes. Alright, so I focus in on the first two terms. I'm going to factor out a negative 4. And so I get x squared plus 6x. Just watch the sign there. Negative times positive gets me back to negative. Plus something minus something. Keep the 20 on the outside for later. Alright, we're trying to create a perfect square. And so if 6 is in the middle, these two terms doubled have to give 6. So this number here would have to be 3. This sign is plus. Squaring the 3 is 9, so I add 9 and minus 9. Okay? Let me just take that away for now because we'll come to that in a minute, but that was just part of my thinking process. So now I want to get this last number here out of the brackets, so I'm going to just write x squared plus 6x plus 9. And the last number would be negative 4 times negative 9, which is positive 36. And that factors perfectly. Perfect square. X plus 3 squared plus 16.